Hello everyone, myself Indradeep Kumar, Assistant Professor in Institute of Aeronautical Engineering. Today we will discuss analysis of aircraft structure, and in that first we will see all the basic concept which requires for structure. Okay, so this is basically for 5th semester student. Okay, so just see in this what we will see. First we will see evolution of solid mechanics. That means from where that solid mechanics came, because that is the basic things which required for structure dynamics. Then about the history of the background, like aerospace structural analysis, how they analyzed, from when and which type of aircraft structure is required for what type. Then next we will see first controllable human flight, that is just in use, or first what they prepared. Then after that we will see the basic development of the aircraft structure. Then we will see the importance of a structural design analysis. In this we will see how the structural design will vary, or it depends on the stability of the aircraft, or you can say either it's a passenger aircraft or cargo aircraft, how that design is important. So let's start. So first we will see the introduction. So Galileo in that time itself given the concept of stress. That means that is the most important thing when an aircraft is flying. So concept of stress means when load acting on anything, that is the just force per unit area, you can see that is the stress. So how they determine, because aircraft having the area, surface area is there, on that some load is acting, that we will see later which, how many types of loads are there on that. So first they given the concept of stress. So they found experimentally how they are experiencing the stress because of tension. Then in next, mathematical and physical studies were carried by Isaac Newton. So now stress they given the concept by Galileo. Later that is analyzed mathematically by the Newton. Okay, and by introducing the laws of motion. So already we know that 3 laws of motions are there. So here they introduce the laws of motion. Then next, Robert Hooke and E. Marriott observed that displacement is proportional to the applied load for many materials. Means what? When we applied the load, definitely something will displace. How? Suppose here, if from here to here, if it's displacing, by applying the 5 kilonewton force, right? Now, if we will apply 10 kilonewton force, then instead of from here to here, this will move double of that one. So he introduced, depending upon how much force we are applying, that is the proportional. If suppose 5 Newton we will apply, then 1 centimeter if it will move, then by 10 kilonewton it will move for 2 centimeters. So that is directly proportional. Then Bernoulli is given that how deformation occurs. Means if suppose same thing like 5 kilonewton we applied and that body got deformed, whatever the amount of deformation is there, if we will apply 10, that is twice of the load, then the deformation will be double of that one. He again given the concept of stress and strain under the tension. Now the thing is, what is strain? So strain is nothing, it's how much the elongation is there. Like suppose from here, this length is 1 meter. After pushing or pulling, that also we can do, right? So once if suppose 0.01 mm change is there, right? So 0.01 mm is the elongation in that one. So now the total length becomes what? 1.1 meter into 0.01 mm, right? So this total is the now new length of the beam over where we applied the force. So strain is change in length, by how much it's changed, this amount. This divided by the original length will give you the strain. Now next, you are given the linear relation between stress and strain. So now the linear relation means what? Just like we are saying linear equation or linear, that is, this should be, when we plot the curve, this should go straight. Either in this way, this also, but this should not like curve. So according to that, they given linear relation, and later it's modified by the Young's modulus, and that is only they given as stress is directly proportional to strain. Means what? Stress, if stress will increase, then strain will increase. And here, when proportionality constant came, like stress is proportional to strain. So for removing this proportionality constant, Young's introduced that Young's modulus of elasticity, which is represented by A. So now the same thing becomes stress equals to E, that is Young's modulus, and the strain. So we are representing this stress as sigma equals to E, Young's modulus of elasticity, and into strain. Right. So first it's given by Euler, later it's modified and used by the Young's. The next is internal tension acting across the surface. Now once the push or pull, that means when we applied the stress, definitely the deformation will be there, that is internally and externally. So how internally they deform, that is given by Gottfried and Leibniz in 1684. So from that time itself they identified how the stress will be there. Now again Euler introduced what? Compressive normal stress as the pressure in fluid. So now the thing, compressive normal stress. Compressive means what? When we are compressing. So compressing means, suppose this body is there. So we will apply the force like this. We will apply the force like this. So now we are compressing. So when this is perpendicular to that one, just see the normal stress. Normal always stands for perpendicular. So when these force will be perpendicular, if we will like inclined also we can do that one, right? But that won't be a normal stress. That should be perpendicular to the surface where we are applying the force or stress. So that normal stress and pressure in the fluid. So same thing, when we are talking about the solid, that time we are saying it's a stress. When we are talking about the fluid, either it's a gas or liquid, then we are saying that is the pressure. Formula is same like applied force per unit area in case of solid also, applied force per unit area in case of liquid also. The thing only is for solid we are measuring stress, and for liquid, that is fluid, either it's a liquid or gas, we are saying it's a pressure. Then later Coulomb's apparently shows that relation between how the beams are there, that is theory of a beam as a bent elastic line. Now the thing, bent elastic line. So when we apply the force according to this, it's just S equals to what? That just we had seen, sigma equals to E, this one. And according to Euler, what they said, it's the linear one. Now later they found no, it's not linear. Up to certain limit only it will be a linear. After that it will bend. So how it will bend? So first like this. So first it will go like this, and after certain limit it becomes like this. Even after applying the force maybe it will break that one. Just take an example of elastic. We will stretch, if we will release again it will come back to their original position. So till that there is no deformation, we can say it's in elastic limit. Means from here to here just apply force, and after this release the force, they will come automatically to their original shape. Then we can say this is in the elastic region. Now from here to some, just extend some force again. So what happened? Then here that will come, and if suppose now some deformation will be there, okay, till that deformation we can see it's in plastic region, just like balloon. If we will blow the air inside, what happened? After even releasing the air, then also some deformation is there. So that is the plastic region where some deformation will be there. Again, if we will apply the force or stress, then what happens? This will increase, and at certain time, that is up to the maximum limit, after that it will break. So they found till in starting they found up to this only, that is linear. But now what happened? After elastic limit, they are not linear. Now this becomes curve. Okay, so that's why it's a given bent elastic line. So now here this is the elastic region, and after that now this is bending. So this is just again given by what? Coulomb. Now James Bernoulli later proposed that the curvature of the beam. Now curvature means what? It should be curved. So like suppose here beam is there, like this is beam. Now we will apply the force, right? So at certain limit what happen? If suppose this we will apply, then or just take this one. If suppose this is the beam and we are applying force by this side and keeping this fixed, then what happen? this will bend like this. Up to this it will be straight, and this will be bent like this. Right. So from here, this will be straight. Only this part will bend. If from here it's fixed. Now, if this is not fixed, then what happens? Suppose let's apply force from here. Then this beam, same beam, will be like this. Okay, depending upon how we are applying the force. So that's why they given as the curvature of the beam. Now the straight beam, after applying force from both the sides, now it's not straight and this becomes the curve. So curvature of the beam. How much it will bend, that is what? Again, it's proportional to the bending moment. Okay, how much force is applied? Force into perpendicular distance is the moment. So how much bending moment is applied? According to that only this will bend. Now again, Euler and Bernoulli is given the theory of what? Transverse vibration of the beam. Now the transverse means once we applied the force, definitely, like suppose any utensils is there, if you will hammer with the spoon also, you can see it's just like it's vibrating something. So from there only they just given the transverse vibration of the beam, means when it will vibrate, or after applying the force it will vibrate perpendicular to the. Euler again given when? Now in 1757, that buckling of initially straight. Now this one, just same here, buckling. This is straight. Now instead of that, this straight becomes slight curve. That is given by Euler. So buckling of initially straight means what? Whatever the initially it was straight. Now after applying the straight, this becomes buckle. So now this one was straight. After applying the force, this got slightly bent, and that is the buckling of the beam. Okay, subjected to a compressive load. So now what? Here also I given just example. Both sides if you will apply, then this will bend. So given by Euler in 1757. Then in Bernoulli and Euler again in 1742, they given what? Strain energy per unit length for a beam proportional to the square of its curvature. So strain energy, the first thing is strain energy. The energy is stored by the body up before the deformation, means and up to what they can sustain the force. After that, if you will slightly increase, then what happens? That beam or body, whatever is that will get fracture or break. So the amount of energy is stored before this one, that is called the strain energy. Now it's obvious, depending upon how much length is there. If shorter length will be there, they can store less energy. If bigger length is there, they can store more. So that's why strain energy per unit length, up to what length we are applying, is proportional to what? A square of its curvature. Now how much it will form this curvature, right? So that will be the square of the strain energy per unit length, and regarded as the total strain energy, right? So strain per energy per unit length is directly proportional to what? Curvature, which is named as the total strain energy. Now analogies of this is what? Just this we can say as the potential energy. Like, why? Potential energy what? Potential energy is regarded with the datum, means at some height. If suppose something here surface is there, and if you will keep suppose anything over this one, then with respect to this surface, this body does not have any potential energy. Right. Now instead of this, just take this body here. From this surface, how much height is there? Whatever this height is there, and mass of this block is m, then the potential energy in this case is mg, and if this height is h, then h. So it depends on the height. If height is 0, there is no potential energy. Same thing here. It's just like if vibration is there. If this will bend, then only they will have the energy. If this not bent, if it's a straight, means there is no what? Strain energy, because there is no strain. No strain means no strain energy. So this is the case. There is no strain energy. When they have the strain, means they expanded by this, that is h, or there we are seeing delta L expansion. So they will have the expansion means height change. Height change means they will have the strain energy, and that strain energy is analogous to the potential energy. Now, the principle of virtual work introduced by what? John Bernoulli. Now, the virtual work, what we can say? Virtual means what? We can just see. It's not there is no output or we cannot see any work is there. Generally, we are defining work as force into distance. That means how much displacement is there, that much only work we did. Now, suppose if we are applying the force on a wall, can we move the wall? No, we cannot. But after some time, we feel we are tired. We are losing our energy. So where that energy goes? And according to the law, energy neither be created nor be destroyed. So means definitely somewhere that energy goes. Where that energy goes? And what happened to that energy? What we applied on the wall, right? So because of that only, what happened when we will push anything, then our muscles got stressed. So that energy applied by the wall, according to Newton's third law, what happened? That energy is stored in our muscles, and that's why we feel after certain time that either we are tired or we feel pain in that one. So that is only what where the work has done in expanding our muscles. So our muscles expand means there we cannot see that work is there, but definitely work is there, and that type of work is called the virtual work. Means there directly we cannot see the change of the position of the whatever the substance is there, block or anything we are moving, and it's given by John Bernoulli. Euler rendered the energy stationary. Now the thing stationary means which cannot move. So now this energy again after this only they given that energy is stationary. It's not necessary that energy should move. Like here, okay, this at this height, suppose this is, so here is the surface, and now object having 2 kg mass, okay, and this is at 5 centimeter. So total weight will be what? 5 into 2 into g. That is, you can say 10 g will be the potential energy at this point. Now just move this here at 3 centimeter. Now what happened? 2 into 3 into g. So now this will have 6g, only the potential energy. So it depends on what? The height, that is the change in the position. So here, that is now at this stage, when this starts moving this one, now where that energy goes? Once this block is here, that time this will have 10g. Once this move here, now having 6g only. So where that 4g energy goes? So while moving, this potential energy converted to kinetic energy, and because of that kinetic energy only they will have the velocity, and with that velocity they comes down and they loses the 4g energy. So similarly here also, if that energy associated within the body, it's not changing from one place to or by this one, like internal energy is the that is energy stationary is there. So internal energy of any body, we can say that is the stationary energy. Later they developed in what? Calculus of variations, means how these things will vary. Their calculus they given for the equilibrium and when that is in the motion. Now elasticity general theory. So now as I explained, up to the certain limit it's in the elastic region, and after that it goes to the plastic region. So linear elasticity as a general 3-dimensional theory was first proposed by Cauchy, Navier and Poisson during the 1820 to 1803, and because based on that only the Navier-Stokes equation is there that we will see later. So they only proposed what? How the linear elasticity in 3-dimensional it will work. Here what we are plotting in 2D only, right? So they proposed in 3D how this linear elasticity will behave. Now in the isotropic case, it predicts that there is only one elastic constant, and that is the Poisson's ratio. Now after that they just given us what? In isotropic case only one elastic constant is there, okay, that is the Poisson's ratio, and has a universal value of 1/4, that is 0.25. That depends on what? That is the universal value, but it can be different depending upon the condition. Next is maximum possible number of independent elastic moduli. That elastic module, so elastic moduli, in the most general and isotropic solid. Here for isotropic it's a 1/4, but in isotropic, just now I told you that it's depending upon the condition, their value also change. So now if suppose that becomes anisotropic, then who invented that one? George Green. Okay, that is maximum. It's not necessary that 1/4 only is there, that may be many, right? So now how much? Just the existence of elastic strain energy required that of 36 elastic constants. So now let's see, 36 elastic constant for an isotropic is possible, but for an isotropic, Poisson's ratio only is there, right? Relating the 6 stress component, 6 strain component, so 6 and 6, 12, at most 21 could be independent, right? So according to this, only they will have the how many? 36 elastic constant. Now, Venant derived what? Torsion of non-circular cylinder. That is, if cylinder is not there, just like a rectangular cylinder type. Generally, what we are considering cylinder as this one having circular cross-sectional area, right? If it's non-cylindrical, then what happened? Venant found the solution for that also, which explains the necessity of wrapping displacement of the cross section. Wrapping displacement means now this is circular. If suppose now this circular becomes what? Rectangular or a square. So this circular only we are making rectangular and a square. So now just see, if first it should be circular according to the cylinder. Now this what we are doing here, we are making this to either rectangular or square. So let's see, wrapping displacement means what? This is the extra part, right? You can see up to this is there. Here also some extra part will be there. Here also. So these things all should merge here, and then this becomes, that circle becomes the square or rectangle depending upon. So that is the only what? Wrapping displacement. Now we are wrapping this circular, all the extra part in this to form a rectangular or a square shape, and now that becomes the square B. Rudolph, again the given solution of what? Deformation of elastic solid. Elastic solid means what? Up to certain limit, like we hammering, iron is there. So once we will start hammering, it's getting converted into sheets. But now what happens if suppose glass is there? We will hammer it. What happens? Instead of becoming a glass sheet, it will break into many pieces. Okay, so they just given by what? Rudolph, that is deformation of elastic solid. So how much elastic? That means iron having more elastic property compared to the glass. Glass will break easily. Now, solution for stress and displacement due to concentrated forces. Now, concentrated meaning what? At one point. So instead of like here, if suppose force we are applying from here to here, so this is called distributed and uniformly distributed. At this point, whatever the amount of force is acting, the same everywhere force will act, then we can say this is uniformly distributed. Now just suppose if this is 10 kilo Newton meter. Now this take whole force and just apply at one particular point. This whole thing, whatever the amount is there, that at one particular point, then we can say this as 10. Then this is a concentrated load or point load. So now concentrated force acting at an interior points of a full space were derived by Kelvin. So now inside of the body, whatever the force will be acted, that is again found by what? Kelvin, and on the surface of a half space by what? Cerruti and Sinks. They found over the half surface, Kelvin found for the full surface. Postman had analyzed vibration of an elastic cylinder, right? So in elastic cylinder, how the vibration will be there, that is analyzed or discovered by the Postman. And Lamb and P. Jerris derive the equation for what? General vibration of elastic sphere. So for elastic cylinder, who found that? Postman. And for the elastic sphere, their equation found by the Lamb and Jerris. And then in 80 1880s. Next, Green and their team in the mid 1800s, what they developed wearable theory with the form of stress strain relation for a specific rubber material. Now just see here, rubber type material. So now later in mid 1800, who Green and their team found for the rubber type of material also. Before that, it's only whatever the metal or cylindrical those things are there. They found like for cylinder, sphere. Now rubber. That means once we will expand that one. After that again it will come back to the original position. Like iron sheet is there. Once we will hammer it, you cannot convert back to the original position. Now that becomes in the form of sheet. But in case of rubber, what happened? Once we will remove the force, they will come to the original position. So that found by the Green and their teammates, they have the large elastic deformation. Meaning what? Even after stretching more and after releasing, they will come back to the original position. But in case of iron or any metal, once you will hammer it, you cannot convert it into the back. Again, you will hammer it in opposite position. If it's possible, then only that will come to the original position. But after releasing the force, it won't come by their own to the original position. So rubber having a large elastic deformation. Now, non-linearity of simple problem like torsion and bending. Now, bending is what? We can see the bend. But what about the torsion? Suppose if this is there, right? So now bending is just we are bending. So this will becomes like arc. Now torsion is just twist. Instead of this, now make twisting. So bending and twisting is given by what? Ronald Rivlin when in 1940s to in between that 1940 to 1950. So just see here, Leonardo da Vinci given the concept of a flying machine. So that was the theoretical. According to that, they only started making, okay, but still they fails many times. So these are the just what they predicted. Okay, this type of machine should be there. So just see, this is the first flying aircraft given by the Wright brothers that everyone knows. First flying aircraft is what? By the Rutherford. This is controllable flight, not first flight. They tested many times before that also. Controllable flight by the Wright brothers when in 93 in North Carolina. Now the thing, how much they flight. So their endurance 120 feet. That means it moved up to 120 feet height, and for 20 seconds it flies. That is distance covered 120 feet, and 20 seconds it flies. Mankind for a century has dreamed about doing or try to do what the Wright brothers accomplished in 1903. Later that what we are doing, we are just what Wright brothers did at that time. We are just improving that one and trying every day to improve. Okay, now we are even not using this one. This one definitely we improved. So again and again we are improving that one as much as we can improve. So that much either it's a cost effective, it's a safer. Okay, so we are working on that. Now some old, this one what they used at that time. So let's see, range and endurance of this one is 120 feet unlimited. Okay, Hal Japier the name, 336 hour 22 minute 8 second. That was the flight time of flight. How much payload is there? One person was there. Two, that means 1 person to 525. Option is that A380 to 800. That flight we are giving the name according to that, like Boeing 737, Boeing 738. So same A. So how much their capacity is there? 250 ton. The volume of that is what? 1100 meter cube space they have. What is whom? Antonov. We know that world's largest aircraft. Now even though that is not more than last year only that got, but that was the biggest, or you can say largest cargo aircraft, okay, having the capacity or payload of 250 ton. 250 ton is what? 250 and 1 ton is 1000 kg. So just add 30, right? That much weight that can carry. Okay, their speed is 10.98 kilometer per hour. Okay, to 3529. Just see a 3529 kilo. Whom that having the speed of Lockheed SR-71. So that up to this speed it can go. Their name is Blackbird, and 28,000 kilometer per hour. That space shuttle Columbia. So just see the speed that can be fly by almost 11 kilometer per hour also to 3529. That means almost 3,530 kilometer per hour. That is supersonic type. And even 28,000 kilometer per hour also the speed of shuttle Columbia. So now just see from there here just now here with this what we are doing, we are improving. So improve to, that means from 10.9 kilometer to we reached 3,530 kilometer, and in case of a space shuttle we reached even 28,000 kilometer per hour. So from 10.98, that is 11 kilometer per hour, to 28,000 kilometer per hour we achieved. Even we can do further more also. So improvement is again going on. What was the wingspan? That is 12 meter, okay, to 79.8 meter. Again 79.8 meter is for a 380 to 800 to 88.4. That is for again Antonov 225. So that having the largest wing span. So earlier 12 meter was there. Now we reached up to 88.4 meter. Super heavy. That how much? That lift launch vehicle. Even one aircraft is there that carrying the what space shuttle to launch. Okay, so that is Saturn V. Height is 110.6 meter. Diameter is 10.1 meter. Just see the mass. Okay, 29. That is 2970 ton. Almost 3,000 tons. That having the mass. Now come to the structure, how it's designed. So this is what you can say, this is the shape of the internal shape of the wing. Over this what we are doing, we are putting the alumina and we are covering to provide the strength of this one. So these two are the internal view of the wings, and this is what the, you can say, the fuselage or cabin where we are sitting. So now just see, this is, suppose this is the gate through which we are entering into the flight. Over this surface all the seats and are there where we are sitting. Now here just see, this is the over this, or you can say this is the overhead, that is cabin luggage where we are putting, and below this seat all the cargo they are putting. So that cargo also should be arranged properly so that the center of gravity of the whole aircraft should maintain. It's not like that they will put here all luggage and backside it's empty. No, this should be distributed throughout. So to maintain this aircraft or structure stability also. So these things must take care while filling the luggage, or while even first when we are manufacturing the aircraft, that time it's very important, and after that also during the flight these things also should be take care. Then only the center of gravity or the aircraft will maintain and that will fly smoothly. So later we will see in the detail what is these things what we are saying. Just see, this is the this should be the aerodynamic stake. Okay, so these things we will see in details, how, what is the name of this one, this, everything we will see in details when we start the module. Now come to the load. What are the loads acting on the aircraft? So first, when they are on the ground, that means before the flying. So what all the loads during the movement and transportation is what it's like. Suppose it's in the where in hangar, that aircraft is there. Now from hangar to the runway, once they will move, they are sometimes they are moving by their own, sometimes some vehicle is there that is pulling to the runway, right? So at the, that means from the hangar or where that aircraft is there to reaching to the what runway, okay, that comes under what? Taxiing, towing, hosting. So these are acting on the ground. So taxiing means moving towards this one. Towing, that someone is pulling or towing that one, and hoisting. So these loads acting on the ground, that is not by other, that on the aircraft only, either that will move by their own, that is taxiing, moved by something, towing, and hoisting also. So these three are at the ground only they are experiencing. Now so once up to this one, once they will fly, now that came in the contact of air. Now air have the major role. So in air what they will have, so just see, imposed to the structure during flight. Yes. Okay, by maneuver and gust. What are the things that we will see? So in that only now that comes to the like in cabin how much load is there. Okay, so let's see here. Aircraft are subjected to catapult takeoff and arrested landing load. Now catapult takeoff means what? Suppose here two fixings are there, here something is there. Now aircraft will come and like they will pull and they will release suddenly. So with that this will move. So now here again this will act like a force. This one first. Now at the time of landing, even you can see in the movies and all, what happened over the ship. They are landing there, one iron type rope wire is there. Okay, that wheel is touching to that one and then only they are holding. Otherwise, because on the ship they don't have that much longer runway, so they cannot land properly. So for that only this cable is used to arrest the speed. Okay, and that is only named as arrested landing. So most large civil and military aircrafts have pressurized cabin. Okay, even once you will enter into the aircraft, you can see some smoke type is there, and that's why just because of that pressure only at higher altitude, what happens? Pressure reduces. So they are pressurizing so that we are comfortable in that one for the high altitude flight. Now further, what happened? Surface force which act upon the surface of the structure. Later we will see all the details in this one. That is dynamic and hydrostatic. So hydrostatic means what? Because of the pressure of the air, right? Dynamic means because of the movement of the aircraft, right? So this will be there. Next will be what? Body force which act upon the entire volume of the structure. Now just see, this part is there, right? So definitely here some material is there, here some material is there. So their weight also act vertically downward, that we know. This also is there, this will act vertically downward. So every part of this will act vertically downward, right? So where they are in contact, this weight will, suppose this part is there, right? Or from here to here everything, or like suppose seat is there. Seat weight will be over this surface. So now seat weight plus this will act vertically downward. So first seat weight will act vertically downward, which is associated by this. Now the overall weight will act vertically downward. Okay, so like this only the entire weight of the structure body. So that's why this structure we are studying, or we will study how to reduce the structural weight, but make sure the strength should not decrease. That means we have to increase the strength to weight ratio. So even in less weight, more strength should be there. Okay, that we have to keep in mind when we are dealing with the structure of the aircraft. Then gravitational also is there, where the load will act mg. So their gravitational force also will be there. Now, so these are the loads what is acting. So now just see here all the stuff. So here wing is there, right? So wing produces lift. So on the wing, lift will act vertically upward. So this also is wing vertically upward. Now overall weight. So here suppose if center of mass of or center of gravity of the aircraft is there, so weight always act at the center of gravity. So aircraft weight will act vertically downward. Now just now we are seeing because of the dynamic, that is because of motion. So once this will move, so a yawing moment will be there. Moment is what? Force into perpendicular distance. So after rotation, yawing moment will be there. Now this is moving forward because of the thrust produced by the engine. So one force will act opposite to that one, that is called only the drag, which resists the movement of the aircraft. So drag will act always but backward or opposite to the movement of aircraft. Now next is horizontal tail plane for pitch control. Now pitching is what? Suppose moving left, right, then this will be there. So again on this, what happened? Force will act. Now this is the vertical tail plane for directional control. If suppose this need to go left, then this will turn, go right, then this will turn this side. So these forces acting on the aircraft for smooth, or you can say the safe flight. If any one of them will not work properly, suppose this side is not working properly and we have to move left, we cannot move left. Always this will go either straight or, this move to right means always this won't come in this direction because this one is not working. If suppose this one is not working, then we cannot go. So every one should function properly, then only we can either safe, maneuver or land. Okay, so now these all loads based on the pressure distribution, lift also how it's producing because of the pressure difference. At the upper wing, low pressure is there, and the lower wing, high pressure is there, and because of that, pressure difference is there. So lift generated. So all these forces is due to the pressure distribution, or you can say the pressure difference. Let's see. Basically, all these loads are the resulted from the pressure distribution over the surface of the screen produced by STD flight or maneuver or gust continuous. Whatever will be there, their pressure distribution or pressure difference will be there. And because of that only, just now I said here, this shape, to minimize the pressure distribution only, or to just, so it should not separate from this one. Okay, we are using the aerodynamic shape that we will see later. Now, so let's see. Generally, these loads cause direct load, bending load, shear, and torsion. So this is just like this one. This is the direct load, that aircraft weight is the direct load. Torsion means, just now I explained that if we will twist it, that is the torsion. Shear. Shear means over the surface, whatever the load will act, that is called the shear. Okay. Pressure on the surface, whatever the force will vertically act, that will be the pressure. So bending load, because of, if suppose this will bend, that already we discussed. Direct load, it's acting on the body just like air is sitting. So that is the direct load. Okay, these are, and in addition to not only these direct loads, but local load also, normal pressure load also imposed or acting on the screen. So we have to take care what all the loads acting because of pressure distribution, then direct load, and then what local, normal, these things also we have to take care, and according to that only we should what prepare the structural material, structural design, okay, so that it can sustain. Now loads, how it's the varying. Okay, so let's see here. So this is the leading edge, this is the trailing edge, and this is the aerodynamic shape. So here CP, that stands for center of pressure, and from here only the vertically upward lift will be there. So what I said, that at low pressure is there, right, that high pressure is there. So now just see all the pressure acting towards the what, this wing, right, towards this wing they are acting. Okay, and now so just see in this lesser area only they act. So lesser area means more pressure applied. Here at the upward they are acting vertical, this one upward to the surface, right, and that's why, because just see this also moving upward, this also moving upward, and finally this moves upward. So at the leading edge, at this stage only where this is there, that is the stagnation point. Okay, that we will see discuss. So here it won't be there, some will be here and here, and because of this difference only here lift generated and moves upward. Now the thing, just see how the drag is produced. So this force, this will be their pressure difference, and it comes to like this up to this part here, not over the this one. So here means what, bottom part having the higher pressure, so here higher pressure generated, or because of the separation of this. Okay, so here drag produced, and that's why drag is always acting opposite to the or backward side to the motion of this one. So the same only you can see here. This is AC, that aerodynamic center. This is CP, center of pressure. Here MO is moment. Okay, this is drag. So drag always will act in this direction. Lift will act always vertically upward. Okay, so these forces are called what? Aerodynamic forces, which is acting on the aerodynamic structure or shape. So the force on the aerodynamic surface, that is wing, vertical or horizontal tail, result from a differential pressure distribution caused by incident, camber or combination. Okay, so by this only incidence happens, camber or combination, whatever is there, like symmetrical, unsymmetrical aerofoil. So this, because of this is there. So all these comes under aerodynamic surfaces. Now again just see here. Now span wise. So this was only for wing, right? So now this is the what, fuselage from the front view of this one. So here just now we had seen at this it will be less, increase over this one, because over that the flight is there, right? Flat surface, this comes under, and then again this side also. So from both the side you can see it's increasing towards the fuselage. Okay, so this is the span wise load distribution. How this is there over the surface, now just see here. So from here, if because this side it's moving like this, it's going. Okay, at every point like this it will be there. At this center of this almost it will be maximum, and this will decrease in either side. Now here if you will see, because of how that lift generated, so I just see here. So these are the what, chord wise, and this is span wise lift distribution. Okay. Now here you can see the total load acting, or just the other loads are what? Other loads include engine thrust on wing or fuselage, which act in the plane of symmetry, but may, in the case of engine failure, cause reverse fuselage bending. So now you just see here how all the forces other than those important forces, these are what we have to take care of these forces also, but at the time of flight we are not considering that much. At the time of structural design these things also will be there. Okay, so we have to take care of that one. What? So just start from here. So this is positive dynamic gust and lateral gust. So here they will feel this one. At the top surface they will feel what, or they will experience gust. Again on the wheel, definitely wheel is there, so wheel also will experience the forces. So this is landing gear for what, taxiing or towing load will be there. Here positive maneuver will be there. Upper surface, because of that only this moving up, so upper surface negative maneuver will be there. Again on the wing, positive will be the upper will be the positive, and that will be the static gust. Negative maneuver will be the backside of this one. So here aileron, once it will flip or roll, that aileron roll will be there, because of that again load will be there. Same here, backside the yawing will be there, so because of yaw maneuver load will be there. Okay, now here because of this change, here the buffet load will be there. Okay, here the lateral maneuver will be there. While taxiing, this side also load will act. So these are the loads other than those important loads also acting on the aircraft structure. So depending upon where, like suppose taxiing is there, then here we have to take care. Even you can heard in news and all, like that tire got burst or it's got slipped. So here because of this only that is there. So every part is important, from toe, or you can say from this to this, while making the aircraft structure. Now how it's working, that is function of a structural component. So first let's see the basic function. First one is what? To transmit and resist the applied load. Means what? Resist means what? It's okay, after applying the load it should not break. But what about transmit? Because up to that we have already seen the energy is stored, that is strain energy. So up to certain limit only they can store the energy. After that what happens? It will break. Right? So they should not store energy, they should transfer one body to another body, or yeah. So if suppose this will experience the force at this one, they cannot absorb energy much more, right? So what happens? They will transfer to the adjacent one. This is there, right? So this will transfer to this one. This will transfer to this one. This will transfer to this one. Like that they will transfer. Okay, so that because this comes when air strikes, so this part will first hit the by air, right? So all the load will be acting on this one, right? Internal part, what happened? Nothing. Over the surface, if it's there, then also the upper part will act. So they will transfer the load to the inner part also. So that's why transfer of load is also very important. So structurally we have to take care of that one. So they should, that means minimum component we have to use so that they can transfer the load uniformly and they can resist the breaking of the structure or damage of the structure. That is the first. Next is to provide the aerodynamic shape. That also should be in aerodynamic. It's not like that any block body or any particular shape you can give, right? So that also you have to take care that aerodynamic shape must be achieved. As much as that will be perfect, we will get that much improved efficiency. Next is what when we are making the aircraft for what? It's not like that, okay, just we make the aircraft and just keep somewhere. So definitely we will use means what? Either for carrying the passenger loads or anything. So to protect passenger, that passenger safety also should be there, payload also, then that the whole system. Okay, so these things should be. So to protect passenger, payload, system is what? All inside this one is there. It's not like that, okay, passenger is safe and once you will land you can see the backside, or this one is not there, or wing is not there. So that those things should be safe. Okay, from the environmental condition encountered during the flight. Sometimes weather is not good, or any air gust is there, or sometimes even you can see the bird hitting is there, bird hits. Okay, so for these things that should be safe. So that comes under the basic function. Now the requirement in most aircraft results into a cell structure that already we had seen, where I explained. Okay, so why that cell structure is required? So just here, the outer surface or skin of the cell is usually supported by longitudinal stiffening members, then transverse frame to enable it to resist bending, compressive and torsional load without buckling. So these things already I showed you the how the buckle will be there. So that should not buckle. That should be straight, whatever the shape and that time used. So up to that only they can resist. Means definitely the force should distribute. If force will not distribute, that individual member of that rib or anything will experience more load and finally that will break. So they must be distributed. Next is what a structure should have, that we are using what? Semi monocoque. Okay, while thin cell which rely entirely on their skin for their capacity to resist load are referred as monocoque. Means substructure as semi monocoque and the main structure should be of the monocoque type. Now just see here how this is there. So this is the upper part that is covered by the skin, right? This is the rib, right? This one is the longitudinal stiffener. Stiffener means what? Just stiffening. Though even after some they are experiencing the force and then they are trying to twist, this again they should come back to the original position. So this is the longitudinal stiffener. Super wave. So this whole the vertical one, not this empty space, this one, right? So this the vertical one is the super wave. Rib is here, from here to here, whatever is that, right? And this upper one, this is a spar flange, just like this one. So these are supporting element to the surface of this one. Over that we are putting the alumina sheet. So that is the skin of the aircraft. So now transverse wave. Again, this we had seen this one, wave, super wave, and these things that is required. So see, these follow and maintains the aerodynamic shape. So you have to arrange like this. So they must maintain the aerodynamic shape. It's not like that we can arrange anywhere. Okay. Now the second thing they use is to resist what, or to withstand the skin structure. It's not like that if this will itself move, then definitely the skin won't be in their original position, right? So they act as a skin resisting, okay, and they are distributing the aerodynamic load experienced by the skin. So now skin will transfer to these members and these members will distribute and finally those structure will be safe. Now what is the next use? They distribute any concentrated load, whatever that is, undercarriage and additional wing stored load, means whatever the payload we are adding undercarriage or wing span like fuel and all. So they must be what? Also they should manage, or they should handle with those loads. Okay, so to the structure and redistribute stresses around discontinuities, that is at the door, because it's not like that. Suppose door is closed, once at the landing time or after landing they are opening the door, so what happened, they now, that is not the part of this whole thing, so they are what, distributing their loads. So that type of load also should be take care. Now just see, ribs increases the column buckling stress of the longitudinal stiffener by providing resistance and reducing their column length. So now just see here, rib, here, this one. So instead of from here to here, suppose one longer we are using, so what happened, they won't have that much stiffness. So that's why we are using what, a small part for what, in the resistance. Now here one end is there, here one end is there, so they will resist and they will support the other part of this one. Now column of the length, so suppose if this one bigger from here to here you will use this part, then what happens, this much longer column is required, right? Longer column already, so if longer column is there, then bending will be more. So to reduce the length of the column, now only this much size column is required. So this much size rib, that much size what, column is there. So that's why rib is again, rib plays an important role, okay, for protecting the skin or the structure of the aircraft. Now ribs, it is the outer portion of the wing, that just I showed you in this one. That is, ribs act primarily as former for the aerofoil shape since it is low load carrying section. So now just see here, this also it's like aerodynamic shape, so they are forming only their structure and experiencing what, low load carrying section. Okay, next, an extremely lightweight structure is sufficient for the purpose. So for this part, not that much heavier substances or heavier thing is required. Lightweight also is sufficient to support the skin. Okay, where now nearer the root section, wherever is there, ribs are required to absorb and transmit large concentrated applied load. Just see here. Okay, so whatever the force will act on the screen, they will transfer over this one. So they are what, they are experiencing the large concentrated loads, such as from undercarriage, engine thrust, fuselage attachment points. So wherever the fuselage, like suppose this is there, or here at this point. Okay, so this also should be of aerodynamic shape. So here they experiences the more force. In the middle of the wing, ribs support. So in the middle of the only wing supports at the middle of the wing also. Hinge reaction from aileron. So when aileron under the working condition, then their hinge also supported by this flap and other control surfaces. So these are what, the structural element in the wing. Now come to the wing skin. Wing skin is just to explain, this is the upper part supporting the aerodynamic pressure distribution. So according to that only the pressure, how pressure will distribute. Okay, so this is the wing. From these wing, lift is generated. So at the lower end, high pressure, that means here pressure distribution. So here pressure distribution, that is low pressure will be there. At the bottom of this one, more pressure will be there, and because of that, lift is generated. Now whatever the aerodynamic forces are there, they will transmit this to rib and other parts, and hence those forces again transmitted in the other members. So transmitted to the ribs and the stiffener by the skin. So they are transferring to the rib and the stiffener through plate and membrane action. So they are just connected and they will transfer those forces to rib and not. Shear and torsional load are carried by the skin and spar web. So shear means over the surface. Just now I explained. Shear means what? Over the surface, that along the surface if any force is acting, that is called shear. So now if any force will act like this over the surface, so that shear phase also experienced by skin only. So these also the spar wave when it's connected to that one. So this and spar wave only will, that is this skin force and this spar wave experiences that shear and torsional load. Why? Because torsional means what? Something should be twisted. If this lift will itself, suppose this is lift and this will get itself twisted, what happens? Okay, that spar will again bend. So that instead of after resisting the bending, that will be in the same shape. So now, in case of axial and bending load, what happened? Combined action, skin and longitudinal. So for axial loading, what is that? Skin and stiffener. For tangential, okay, shear and torsional. Now, longitudinal stiffener. That is simply, it's a longitudinally connected stiffener, that is longitudinal stiffener. So just see, these are attached to the skin and ribs, thereby dividing the skin into a small panel. So just see here, this one, right? So this small type, panel type, they are forming and increasing the buckling and failing stress to the skin. Now because of that, the buckling stress will be more less, even they can sustain the more stress before buckle. Now spar wave. So we are discussing about all these elements what we are using in the wings. So first, now spar wave, this vertical one. These resist shear and torsional load. They perform a secondary but significant function in stabilizing with the skin. Why secondary? Because the skin is working as the primary. The skin is experiencing the force. The skin transferring to the spar wave. So now first, it's not direct experiencing the load. It's not air is coming directly and hitting to the spar wave. No. On the screen only they are experiencing the aerodynamic forces or whatever the forces, either it's a gust, they will experience. Now they will transfer to the spar wave, and that's why it's a secondary wave. Okay. Now spar flanges. So here, through which spar is connected. So see here, this is right. So this is not up to this. This will go like this up to this one. Similarly like this. So here. Okay. So spar flanges or cap are capable of supporting large compressive load from axial and bending. So now this also is first thing supported by this one. Second, their work is it's not allowing to bend the skin. Okay. So that's why from skin load is transferring to the spar flanges. So above mentioned structural functions are applicable for wing, horizontal and vertical tail. Already we have seen for these things will be used or we are using in our wings, horizontal and vertical tail. Right. So now just see the total how this is there exactly here. So these small over the wing, the backside, some cuts are there which is flapping over this one. So these are called spoilers. Okay, just see here in this image clearly. So here these are spoilers over the upper surface, that is wing upper surface, not this side. Again, just see you can this side, it's the cut part is there that is moving depending upon the adjustment. So this is leading edge slat. Okay, that we will see what is slat and all, that is in the aerodynamics, that high speed or low speed aerodynamics depending upon our high lift devices, low lift devices, these are there. So these cut parts are that one, right? So over this wing surface, these are attached. So this is the leading edge slat. Now come to this one, angle of air flow sensor. So at what angle air is flowing or coming to this one, they are sensing here, means at what angle the air will hit to the aircraft. A radome, that is the front part of the aircraft. A static port, both sides, that is that one is not moving, that just there. Here pitot tube is there both the sides to measure the pressure, how much pressure or there, how much pressure is acting on the wings or aircraft by those loads. Again static ports, both sides will be there. Then engine intake. Engine intake means what? Through this air will enter into the engine. So this is the engine and intake. So now engine, just here, engine is connected to this wing. So from here the fuel tank will be this one. So from there fuel comes to the engine and it's working. So now this is the wing tip. Even you can see this type is there. That is here. Let's see. This is a spoiler, that side. That is, this one is what? Aileron. Here, this is leading slat. This is trailing as flap. Because it's a at the trailing as flap. APU inlet. Okay, so from here only they are guiding. Now this is horizontal stabilizer. Okay, here at this, just again this cut part is there, this part. Okay, it's not cut part, means cut part, it's aligned, but the movement of this one is there. Whatever these fixed are there, that is not movement. Like this one, wing, this central part is not moving, only this front part and this cut part can be moved. Okay, so that's why they showed here, just like cut part. Okay, this can be movable and remaining this is fixed. Similarly here, rudder. So this part only can move. It's not like that the whole thing move. Whatever this is there, that only can be moved. Okay, and then this is the vertical stabilizer. So from outside, these components are there in the aircraft, but inside many components are there. But generally from the outside, if you will see what are those components is required to maneuver the aircraft, this is there. Okay, these are the reference you can go. Okay, if you have any doubt, you can refer this one, and if suppose you are not clear, you can just comment the question. I will answer you in the comment section itself or during the class. I will clear you all your doubts. Okay, thank you. So if you have any question, you have my mail ID in the first page itself. You can directly contact me or you can comment in the video itself. Okay, I will reply to your answer.
Like, share and subscribe. Hit the bell icon for more updates.